Alright, so we're on section 2.5 and we're going to talk about zeros of polynomial functions. And remember, zeros refers to x-intercepts or solutions of our polynomial functions. So if we have a function and it's a polynomial of degree n, where n, this should say greater than or equal to 1, then the function has precisely that many factors, or n factors. Okay, so we have different types of zeros. We have rational zeros, we have irrational zeros, and we have our imaginary zeros. So determining how many possible rational zeros there are in a polynomial, we can use the rational zero test, where we're going to put the factors of the constant term over the factors of the leading coefficient. And these are possible factors. So we're going to call the numerator P factors of the constant term and Q factors of the leading coefficient. Then we're going to use synthetic division to find the rational zeros. So let's take a look at this first example. And it should say f of x equals x cubed minus 3x squared minus 4x plus 12. And the instructions say to list all possible rational zeros of this particular function. And that we're going to use the concept of P over Q. So remember, P is the factors of our constants. So all possible factors for 12, and then factors of our leading coefficient, which in this case it's 1. So essentially for this one we're just listing out factors for 12, all possible factors. So 1 plus minus 1 times plus minus 12, then we have plus minus 2 times plus minus 6, and then we have 3 times 4. So we have positive and negative values. This is a list of all possible rational zeros for this function. So again, we list out all the factors for our constant over the factors of our leading coefficient, which our leading coefficient is this term. So our leading coefficient here would be over plus minus 1, but we essentially don't have to list that. The factors for the constant in this case are enough. So now that we have a list of all possible rational roots, the instruction says find one of the zeros of the function using synthetic division, then factor the remaining polynomial. What are all of the zeros of the function, and how can the graph below help you find the zeros? Here we can use our graphing calculators to determine at least one of them, and I would say 2 looks like a good candidate, or negative 2. So I'm going to use 2 or negative 2, and notice that 2 and negative 2 are on our list of possible rational roots. And I'm going to use synthetic division to depress it, and then I could maybe factor it, and it looks like it is going to be factorable. So let's begin with 2. So now we're using synthetic division. Bring down your first term, add these two terms. Here we get negative 6, here we get negative 12. And remember here, this is a good check right now to make sure that it is 0. If I don't get remainder of 0, then I know that the point that I picked in here is not a root or an x-intercept of what I was solving. And now I can depress this. This is going to be x squared minus x minus 6 equals 0. And that is factorable. So that's going to be x minus 3, x plus 2 equals 0. And notice that this is in line with the graph that we have here. So our solutions for this, negative 2, 2, and 3. So we have 3 roots, and notice that the degree of the polynomial, that when we started it was to the 3rd power, so I expect at least that many zeros. I do have that many zeros that are rational, and the graph helps us in starting it off. Sometimes we may have imaginary roots, so we won't exactly see them on our graphing calculator, and just keep that in mind. Let's take a look at another. Alright, so here we're going to list all possible rational zeros for, and this should read 6x cubed minus 19x squared plus 2x plus 3. So remember, we list p over q, our possible rational roots, and we're going to put all the factors of our constant, which in this case it's 3, so plus minus 1 plus minus 3. And we're going to put that over q, and in this case is all factors of 6, so 1, 6, 2, 3. And now we need to simplify it, so we have 1, 1/6, a half, a third, then we have 3. 3 over 6 is a half, so we don't have to repeat that. Then we have 3 over 2, and 3 over 3 is 1, so we don't have to repeat that. So all I did was I simplified this by setting up fractions. 1 over 1, 1. 1 over 6, 1 over 2, 1 over 3, 3 over 1, 3 over 6 is a half, so we don't repeat. 3 over 2, and then 3 over 3 is 1, so we don't repeat again. So this is my list here of all possible rational roots for this given polynomial function. So now that I have that, now I want to actually starting with integers, find 1 0 of the function using synthetic division, then factor the remaining polynomial. So the integers in this case would be plus minus 1, plus minus 3. So it narrowed it down for us, which was really nice. So we don't have our graphing calculator in this example, so I'm going to start with 3 and hopefully I get lucky. So let's do synthetic division. So 3. Alright, bring down the first term, multiply them, we get 6 times 3 is 18. Add them, I can already. Alright, so we get negative 1. 3 times negative 1 is negative 3. Add them, we get negative 1 here, negative 3, and we got lucky. So if that wouldn't have worked, we would go to different integers, say negative 3, and see what happens. So here we're going to get to press it, 6x squared minus x minus 1 equals 0. And let's factor. So here we can have 3x, 2x, and we need negative 3 and positive 2. So the rest of our zeros is negative 1/3 and positive 1/2. And I just want to point out, after we have these solutions, that these solutions are in our list of possible rational roots. Here we have negative 1/3, and here we have positive 1/2, and the integer that I randomly picked is positive 3. So our final solution set for our zeros, negative 1/3, 1/2, and 3. So notice that I didn't use my graphing calculator for this example. Again, say 3 would not have worked. I would have picked negative 3, then 1, negative 1. If at that point, because it told me to start with integers, so one of those should work. If at that point that doesn't work, that's when I'm going to go to my graphing calculator to help me get a start of finding which one of these zeros should I actually be plugging into the synthetic division to find the rest of my zeros. Let's take a look at another example. Here we're going to do the same thing, and this time it says the graph below will not help you find the imaginary roots. So notice that the highest degree is to the 4th power, and here I only have 2 roots, and that's why the graph below is not going to help us find those imaginary roots. So in our given, this polynomial should read x to the 4th power minus x cubed plus 7x squared minus 9x minus 18 equals 0. Let's make a list of all possible rational roots here. It's much easier. Remember, that's p over q. The p is the factors of your constant term, and q is the factors of your leading coefficient. So when it's 1, it's easy. We just have to list out the factors of our constant term. So 18 times 1, so plus minus 1, plus minus 18. And then we have plus minus 2 and 9. And then we have 3 and 6. So that's my list of all possible rational roots, and if we look at our graphing utility, it's going to help me out. Because I can clearly see a 0 at -1 and at 2. But notice that none of these other numbers are going to help me finding the other two, so I must use synthetic division to break it down a couple of times, and then I'm going to have to absolutely factor. So let's take a look at what happens. Or use quadratic formula, completing the square once I have x to the second power, once I depress this polynomial to at least to the second degree. So let's begin with synthetic division at -1. That's going to give me 1, -1, 7, -9, -18. Bring down your first term, -1, -2, 2, 9, -9, -18, +18, and now we depress this. And when we depress this, we're going to get x to the third power minus 2x squared minus 9x minus 18 equals 0. Okay, so at this point, if you can factor by grouping, go ahead and do that. And if not, you can depress it one more time. I'm going to choose to depress it, and again, I'm using my graphing utility and my list of possible rational roots to help me. So I'm going to pick 2 because 2 is clearly a 0 here on my graphing utility. So 2, then I have 1, -2, -9, -18. Bring down your first term, multiply them, add them, multiply them, add them, and then multiply them, and we get multiply them, and we're going to get 18, and our remainder is 0. So now that I depress this, remember, if we start to the third power, this is going to go down to the second power, so our answer is going to be x squared plus 0x plus 9 equals 0. And now I have something that I can further simplify in order to find my remaining zeros. So here, subtract 9, then take the square root of both sides, and here's where we're going to get the 3i. So our solution here is x equals plus or minus 3i. So we have 4 zeros, 4 complete zeros, but 2 of them were only rational zeros from our list of possible rational roots. Our imaginary ones will always have to be found through factoring, completing the square quadratic formula. So the list of our solutions include -1, 2, and plus and minus 3i. So we have a complete set of 4 zeros from my 4th degree polynomial. When you have complex roots, I just want to point out that if the solution of a conjugate, so let's say I have 3i, the conjugate pair also has to exist. So -3i also has to exist if it's a root. Or if I have 2 plus 3i as a root, then the conjugate pair must exist as well, 2 minus 3i. And that's what this slide is saying. So if a polynomial equation is of degree n, and then counting the multiple roots separately, the equation has n roots. And if a plus bi is a root, then the conjugate pair is also a root. And then if you look at our previous solutions, the conjugate pairs existed together. Anything else I want to mention before finishing part 1? When you're finding the equation of given roots, what we're going to do is we're going to write the solution as a product, as well as the imaginary root and its conjugate pair, and then we're going to go ahead and FOIL that. So that's what we're going to do on the next video.